Hello, welcome to the technical presentation of Project Smart Museum Management System. In this presentation, we will introduce the design of this system and show you a demo running with Docker containers. Smart Museum Management System aims at making smart crowd management in museum. As the figure shows, the proposed IoT platform follows the microservices designing pattern. Home category is a microservice that manages the registry of all devices and services in the system. Connectors is a set of microservices that allow simulated or real devices to connect to our platform. Control algorithm is a set of microservices that analyze the sensor data and control the actuators in the system. ThinkSpeak is a third-party service that will help collect system data for long-term analysis. Telegram bot will be the user interface of our system. These microservices will communicate with each other with MQTT protocol or REST API. In the design of home category, it aims at implementing four major functions, including the definition of the museum, service registration and query, device registration and query, and dynamically create ThinkSpeak data storage channels. In our system, a museum can be defined in the format of a JSON file. It defines the structure of the museum, including floors, entrance, zones, and the capacity of each zone. With this definition, home category will create corresponding channels on ThinkSpeak using put request when it launches. Once these channels are successfully created, ThinkSpeak will be registered as a service in home category. To register a service or device, REST put request will be used. In a registration information, the register type, ID, component type, and topic are the necessary information. Attribute is the additional information to indicate the property of a device or a service. For example, devices will add their location information in attribute, and during the registration, home category will check the necessary information and attributes is valid or not according to the definition of the museum. Only a proper configured device or service can successfully register to home category. When the registration is successful, home category will return the status and the museum settings in response. Otherwise, registered status and error type will be returned in response. To query the information of devices or services registered in home category, REST GET request will be used. In the URI, we can specify to query services or devices and a specific type of them. And with parameters, we can also specify some attributes of the target devices, which will make the query result more suitable for our target. If we want to delete a registered device or service in home category, REST delete requests can be used. In our current system, there are four kinds of connectors. Every instance of connector needs a configuration file in which defines all the properties of the connector before running. To create multiple instances of a connector, we only need to modify the configuration file. The adaptivity of the system is guaranteed. And all connectors will subscribe to a main switch topic, which means administrators can control the working status of a connector remotely. The first connector we are going to introduce is laser connector. It connects to laser sensors in order to count the number of people moving from one zone to another. As you can see, the laser connector will be assigned with a enter zone and a leaving zone in configuration file. When it is working, it will publish message telling number of people enter its enter zone or leave its leaving zone every 10 seconds. Currently, connectors are also responsible for simulated sensor data generation. For laser connector, you will generate the number of people enter the enter zone or leave the leaving zone randomly. And in this condition, laser connector will also subscribe to a motor topic in order to change the generation mode when the zone is closed or opened. The second connector in the system is camera connector. It connects to infrared camera in order to measure the body temperature of visitors and record the photo of people with over body temperature. When a visitor passes a camera station, his or her body temperature will be detected. When the visitor has a high body temperature, camera will take a picture of him or her, and the picture can be identified with the sequence number. Then camera connector will publish messages, including a sequence number and a temperature value to its published topic. It will also expose a RESTful service that other services can retrieve the photo with a GET request when needed. The third connector in the system is night connector, which is an actuator in the system. It connects to nights in a specific zone in the museum. It can switch on or off the nights and adjust their brightness according to the received message. The last connector in the system is motor connector, which is also an actuator in the system. It connects to motors that control automatic doors in the museum. In the design of our system, different zones are separated by automatic door which integrated with laser sensor or camera. Motor connectors can command automatic door to open or close. In the configuration, each motor connectors will also be assigned an enter zone and a leaving zone. To be noticed, in the closed mode, visitors can pass the door if he or she attempts to go to the door's leaving zone.
This is a flowchart of the overall process. The input of the control algorithm are the sensor data generated by laser connector and camera connector. The final output of the control algorithm will be received by actuators, which are motor connectors and light connectors. In the crowd control section, the crowd control service subscribes to the topic that the laser connector publishes in order to obtain each sensor's enter and exit number information. The total number for one zone would be calculated by adding all enter numbers and subtracting all leaving numbers. The final crowd card would be transmitted to the ThinkSpeak adapter and motor control service. At the door of each zone, lasers and motors are installed. At the main entrance, camera will also be integrated. Each device has its own ID number for data collection and management. Each laser counts the number of people who enter and leave. Crowd control collects all entry values for the same zone and adds them together, as well as the same method for dealing with people leaving one zone. Crowd control calculates the number of people in each zone, saves it in a dictionary, and publishes it to light and motor control. Service of light control aims at changing the brightness of each light in order to conserve energy. It will calculate the best brightness of each zone and then send it to light connector. The control of lighting is dependent on the current time and the crowd control. It subscribes to crowd control messages and controls lights based on crowd size. When the room is empty, it will find the corresponding light ID and reduce its brightness value until it reaches 0, indicating that the light is completely closed. The clock time is the reference parameter for time control. When the museum is open during the day, we don't need a high level of brightness, so the light control service will set a low level. For example, at 8 a.m., a brightness of 40 is sufficient, whereas at 8 p.m., a brightness of 100 is required for a night visit. The purpose of health control is to obtain information from the camera connector and to determine the incoming visitor's body temperature. When a visitor's body temperature is found to be abnormal, the health control service extracts the camera ID and the circuit number and sends it to Telegram to outer monitors. The motor control service will check each room's visitor count to see if it is greater than its capacity. If it is, the motor control service will locate the corresponding motor of this room and turn it off. Message is then published to the motor connector. When a message of abnormal temperature from health control arrives, motor connector will extract the camera ID and find the corresponding motors. Then it sets this motor's working status to closed, and publish the motor work status to the motor connector.
ThinkSpeak adapter is a message broker to transpond messages, and the Mosquito public broker to ThinkSpeak data upload broker. Due to the limit of upload frequency of ThinkSpeak, it will aggregate the target data locally first, and then upload to ThinkSpeak in a specific frequency. During uploading, the aggregated data will be transformed to a stream in the format as the example shows.
ThinkSpeak is an IoT platform to store and analyze data in the cloud. Data is stored in channels. ThinkSpeak provides REST API that allows us to create and manage channels. When start the system, admin can choose whether use the existing channels or create a new one. The REST API also allows us to get data or statistic results stored in ThinkSpeak. Data is uploaded to ThinkSpeak platform via MQTT protocol. Each channel is associated with the zone of the same name. A channel includes 3 fields. Field 1 represents the current people number. Field 2 corresponds to the current brightness state of the light in this zone, expressed as a percentage. And field 3 shows whether this zone is open or closed. In the meantime, we are running an application on the platform, which can compute the average number of people in each hour based on the historical data, to help tourists better plan their travel. In order to show the data to tourists more clearly, we also made a dashboard to organize the data and provide web service. The front end can obtain the sorted data and made some charts and tables through GET request. There are 2 kinds of data, current and statistic. The current data is based on the data category. The value corresponding to name in the dictionary is a list, where the elements are the name of each zone, and there is also a list of various types of data. It can be the number of people, brightness, or on-off status. The statistics are based on zones. The list of corresponding to name in the dictionary is 24 hours, and the data list is the average number of people in each time period.
Telegram bots are third-party applications that run inside Telegram. We can interact with the bot by sending them messages and commands. Telegram server handles encryption and communication with the Telegram API. We could communicate with the server via a simple HTTPS interface that offers a simplified version of Telegram API. In this project, we create a Telegram bot called Smart Museum Bot, which is registered as a service type. It could get statistics from the dashboard via REST service. As an interface of communication, there are different commands for visitors and administrators. If a visitor has a high body temperature, the administrator will receive an alert message from Smart Museum Bot. The administrators could control the working status of the connectors by publishing MQTT messages. Visitors can ask for current and historical statistics, which could help them avoid peak visits. For the administrators, there will be an authentication at first. In addition to viewing the data, the administrator could also control the specific connectors remotely.
The setting of the demo is shown in the figure. Assume we have a small museum with only 2 zones and 3 doors. Each zone has a night connector. The main entrance is integrated with laser, motor, and camera connector. The door and exit will integrate with laser and motor connector. However, the motor connector on the exit will work in exit mode, which only allows the visitors to leave the museum. Now let's see how the system works.
Bye.